One of the debates that occurred for years and years back in the 1970s and the 1980s, and I happened to be a student of Dr. Ura there at the University of Texas, and I remember he was researching this very issue. If you have a continuous beam, does the inflection point, that is the point where you go from a negative moment to a positive moment, does that constitute a brace point or doesn't it? And for many years, a lot of engineers would say, well, gee, there's no moment there. So, no moment, no stress. So, yeah, that's a brace point. So I'll count on the point of inflection as being a brace point. Well, I think Dr. Ura proved very convincingly in the lab and also in analytical finite element studies that he did that the inflection point is not a brace point. And so you say, well, why isn't it? Gosh, there's no moment there. And the reason is, if you look at what's going on, if you just take a continuous beam, and let's just say now, for the sake of argument, there's no top slab or there's no bracing anywhere between supports. It's just a continuous beam. And so the question is, well, there is no top slab bracing anything. Is that inflection point a brace point? And what you find out is that the beam wants to twist like that. And the compression top flange kicks out to the right, the tension flange kicks out to the left, and the whole cross-section twists. So we haven't prevented displacement of the top flange laterally, and we haven't stopped twist of the cross-section at this inflection point. So it doesn't meet our criteria. And so the answer to the question is no. An inflection point cannot be counted on as a brace point. And when you look at a continuous beam, you need to consider the unbraced length from support to support, unless, of course, you have a top slab or something else bracing the compression flange. So these are cases where we're just trying to show you ineffective beam bracing. And one of the things that's important, the AISC specification says that at every support of a beam, you have to prevent twist of the cross-section for it to be a braced point. So every support, if you have a beam that sits on a wall at the support, by the specification, you're required to prevent twist of that section and lateral displacement of the compression flange. So remember that. That's clearly stated in the specification. And then for other brace points along the span, you have to ask the question, have I prevented lateral displacement of the compression flange, or have I prevented twist of the cross-section? Okay, so back to our three zones of lateral torsional buckling. These next series of slides just define the AISC equations in Chapter F for the three zones. Equation F21. In this zone here, where our unbraced length now is less than L sub P, so we're going to say that we can develop the full plastic capacity of the cross-section. L sub P, by the specification, is defined by equation F2-5. It's equal to 1.76 R sub y, the square root of E over S sub y. Again, just properties of the cross-section and the material properties. So if your unbraced length is less than L sub P, you don't have to worry about lateral torsional buckling. You can develop the full plastic capacity. If your unbraced length gets longer and it's greater than L sub P, but still less than L sub R, then we're in this zone right here. And notice that there's a linear degradation of the moment capacity from the full plastic capacity down to a value phi sub B M sub R. And that value divides inelastic lateral torsional buckling from elastic lateral torsional buckling. This linear reduction in moment capacity is defined by this equation right here, which on the surface looks pretty daunting, but in reality it's just a function of the properties of the beam and the unbraced length. And AISC has some aids, design aids in the manual. For instance, that term right there is tabulated in the manual for each section. So, and then there are also beam charts in the manual. For each wide flange beam section, AISC plots the moment capacity as a function of the unbraced length. So it's real easy to just go into those beam charts, and for your particular unbraced length, you pull off the moment capacity. So you don't have to, the ISC's already done all the work for you. You don't ever really have to plug into these equations. And they're daunting looking equations on the surface. You can see L sub P, as we talked about, is that term. I'm trying to get this mouse to focus in. You can see the equation for L sub P. Equation for L sub R is a couple of square roots under the square root, so that's even more complicated. But again, it's all just properties of the cross section. So now, if you continue to grow the unbraced length, you might be getting into a section where your unbraced length L sub B is greater than L sub R, and then we're in what we call the elastic lateral torsional buckling zone. Now, the very interesting thing about this that many engineers don't understand until it's pointed out to them, your capacity, your flexural capacity, is a function of AISC, or is defined by AISC equation F2-3. And if you look at that equation, notice that there's no F sub Y and there's no E in that term. Elastic lateral torsional capacity is not a function of the properties of the steel. It's only a function of the unbraced length and the cross-sectional properties. So it doesn't matter how strong a steel you've got. If you had this 150 KSI steel, if there were such a thing, you would still undergo elastic lateral torsional buckling long before you were able to utilize that extra steel capacity with the higher yield strength. So notice that the bending capacity is not a function of F sub Y when you get that long of an unbraced length. Just kind of like columns too. It's the same thing for columns, right? Long unbraced columns. That L over, if that unbraced length of your column is long enough, it doesn't matter how strong the steel is, you're just going to undergo elastic buckling. Okay, everything we've talked about now was for C sub B equal to 1, and all of these equations were developed. They go back to the days of Timoshenko, who really derived some of these things. You can see all this in Timoshenko's book. But we've been covering the case where you have a beam section, unbraced length beam section, that's subjected to a uniform moment all the way along the span. That is the most severe loading that you can have for a beam, because the entire unbraced length is loaded to the maximum, with a maximum moment. So it has a very strict or very severe moment gradient, if you will. This C sub B factor that we're going to talk about is nothing more than a multiplier to the capacity of the section defined by those previous equations to recognize the fact that maybe our moment gradient isn't constant along the unbraced length, but it's linear. Maybe it's even zero at somewhere along the unbraced length. So think of C sub B as a multiplier that gives you extra capacity because you don't have the severe case of a uniform moment all the way along the unbraced length. That's all C sub B is. It's a linear multiplier to take advantage of the moment gradient. And what you can think of it as doing is going from this lower curve we talked about a minute ago with C sub B equal to 1. Remember the three zones? We were on this curve, this lower curve. Now when you multiply by C sub B, because you don't have a severe moment gradient, we're just raising that curve up to this point. Now theoretically you would go up to here and then go up to there and then go up to there, but I think all of us are smart enough to know that you can never exceed the plastic capacity of the section. That's the limit, and that's why you have that horizontal line drawn across there. But notice that for longer unbraced lengths, C sub B, in effect, is a multiplier that gives you extra moment capacity in recognition of the fact you don't have that severe of a moment gradient along your unbraced length. So that's all that C sub B is. Now, you can prove this to yourself. Just, again, go back to your favorite program, ETABS or SAP or STAT or whichever one you like. Brace the ends of the beam, top and bottom, top and bottom flange. Apply a uniform moment gradient and see what the elastic buckling load is. We're going to assume now that there's no bracing across that flange. That's the case, the uniform moment case, that's defined in the manual. When it says C sub B equal to 1, and here's the moment capacity, that's what it is. Now, if you then go in there and load that same beam, instead of with a uniform moment at each end, you load it with some uniform load where you have a linear moment diagram or a parabolic moment diagram, something less severe than a constant moment across the span, and you go back to your finite element program and you see when that section buckles, and you take the ratio of the capacity with the reduced moment compared to the constant moment, you take those two ratios, and that's what C sub B is. So hopefully that will give you a sense of what C sub B is all about. Think of it as nothing more than finite element buckling solutions that have already been done for you. So you get all you got to do is pick the value. You don't have to run the finite element analysis. Again, you can prove this, as I mentioned, by taking, in this case, I think we took a W18 by 35, and we put a uniform moment gradient across it and find out what its capacity was. Then we put I think we put a uniform load on there and then did it again. And then we took the ratio of those capacities and we got a 2.09. Well, the published value in AISC for that loading condition was 2. So again, it's very close. So C sub B are nothing but tabulated buckling capacities, if you will. Take advantage of this moment gradient issue. So again, C sub B is nothing more than a multiplier to account for the moment gradient. And the point that I'm trying to make here is that the manual and textbooks seem to encourage you to take C sub B equal to 1. You're going to see it's real easy to figure out what your real C sub B is. You may gain additional capacity by doing that. Now, there's several C sub B equations out there, and they've evolved over the years. The one that's in the manual right now is pretty darn good in the sense it's pretty flexible. It covers a lot of situations. It's defined as equation F1-1, but it has a basic assumption to it, and that is it assumes that the beam top and bottom flanges are totally unsupported between brace points. There's your braced here and you're braced there, and there's nothing in between. Now, obviously, that's a worst case scenario, but unfortunately, there are many cases in real life where, and you're going to see that these last two situations, two more C sub B expressions developed by Dr. Ura. This is the case when you have downward loads and the top compression flange is laterally unsupported. This is like if you have a continuous beam with downward load and the top compression flange is laterally supported. A more common situation that we get into very frequently in our long span roofs where we have large uplift loads on the roof. You got a metal deck that braces the top flange, which is great for gravity load, right? Because that's the compression flange. But what happens when you get uplift on that? Well, now all of a sudden our compression flange at the top, the wind uplift is causing compression on the bottom flange. We don't have any bracing down there. But we do still have that deck bracing the tension flange. Well, because of that, this equation F1-1 really doesn't apply. Now, you can use it for that, but that would be very conservative to do that. So Dr. Ura developed these additional C sub B equations for these two situations, and we're going to talk about those. We find them very useful. I think you will too. But first, let's talk about this equation F1-1. This is the one that's in the manual, and it's very versatile, and it's nothing more than an expression that's a function of the moment gradient across the unbraced length. M max is the maximum moment between the brace points, and then M sub A, M sub B, and M sub C are nothing more than the moments at the quarter point, the center line, and the three-quarter point. So knowing the moments across the span, and this value R sub M, which is a new term that was introduced in the 2005 spec, and it's nothing more than a multiplier for symmetry of the cross-section. If you have a symmetrical I beam, R sub M is equal to 1. If you were going to be using a highway plate girder where the compression flange is smaller than the tension flange, for instance, and you're taking advantage of composite action, then R sub m takes on another value. But for most of what we're going to be doing in everyday buildings, R sub m is 1. And so now we can plug into, just knowing the moment gradient, we can plug into and get our C sub b value and take advantage of the fact that we don't have that constant severe moment uniformly across the entire unbraced length. This little table is in the manual, table 3-1, and it just tabulates for you, for various practical load conditions, what C sub b is. And you can see in many cases, instead of conservatively taking it as equal to 1, you get increases as much as 1.14 all the way up to 1.67, 1.3. So that's just a linear increase in the capacity of the section. So why not take advantage of that, huh? And so that's what we're trying to encourage you to do here. Take the extra minute to figure out what C sub b is. We plugged into C sub b for a bunch of different moment diagram shapes and calculated the C sub b value, and it's probably every shape moment diagram you'd ever have in a beam. So just by referring to that, you can pretty well plug off a pretty reasonable approximation to what C sub b is. And notice that frequently they're 1.32, 1.67, 1.56, so you get significant increases by considering C sub b. Now, these other two cases that I spoke of, that Dr. Ura said, well, hey, as neat as this equation F1-1 is, it really doesn't cover some situations that engineers are out there finding in practice. And so he, in his research, he had a PhD student that got a PhD studying these equations and doing a bunch of analysis. And they're very practical. This is the one where, again, you have a continuous beam with moments at the end, at the brace points. The red X's indicate the brace points. And you have a downward load. So you have a beam that has a negative moment at each end and a positive moment in the middle. And so taking your unbraced length, L sub b is the full distance from support to support. You can plug into that other equation there that C sub b is equal to 3.0 minus 2/3 and so on there on the slide, and you will get a good estimate of C sub b for that loading condition. Now notice that the equation F1-1 doesn't really apply here because it assumes totally no bracing between the unbraced length points. In reality, we do have some. Oh, very handy equation. And here's, again, we plugged into a bunch of moment diagram shapes, and we solved for C sub b. Notice that, boy, this equation predicts some really high C sub b's. Well, before you get too excited about that, there are two limiting things. One, the specification says you can't take C sub b more than 3. But the other thing that's going to limit you here is you can never go more than the plastic capacity of the section, right? Once you reach that plastic moment capacity, the section is done all it can do. Okay, this is another series of equations, A, B, and C, that's even more practical and very handy if you have roof members that have high wind uplift. So you folks that are designing metal building type structures that have very low dead loads and high wind loads, wow, this is a cool equation because it'll help you design your roof purlins and even your trusses to take advantage of that metal deck at the top, bracing what becomes the tension flange at the top, right under wind uplift, with the compression flange at the bottom. So having this moment diagram shown here, M1 positive moment, M0 positive moment, M at the center line a negative, now an uplift loading condition. Dr. Ura developed 3 equations depending on what the shape of the moment diagram is. And by the way, in these Ura equations, as we call them, they are sign sensitive. So we're defining positive moment and negative moment as shown, and when you plug into these equations, you have to watch the sign. So we just worked through the 3 cases here to show you how these equations apply. And once again, You can't get these out of equation F1-1 because it just doesn't apply. It would be very conservative if you did that. These are specifically developed for the wind uplift case, and therefore I encourage you to use them. They're not in the specification. I'm not sure why they're not. They've actually been around for 15 or 20 years, and I need to see why that why the task committee in charge of Chapter F hadn't put them at least in the commentary. But they are identified in the literature, the work of Dr. Ura and Dr. Hellwig, now at the University of Texas. So I feel very comfortable in using them. I've had questions about, well, if they're not in the spec, can you use them? Well, it goes into that engineering judgment sort of thing. So now, just a good rule of thumb to remember, if you have a simple beam on a roof that's braced at the compression flange by a metal deck, and you have wind uplift on that, rather than taking the unbraced length as the full unbraced length L sub B and plug it into F1-1 equation, you can just assume C sub B is equal to 2 right there, right away. That 2 is what I get out of that Euro equation. And so these are some practical moment diagrams you frequently get. If you were going to do a roof purlin, simple beam, and you wanted to brace it at the third points, let's say, well, what's happening there is you almost have a uniform moment across here, right? So that's the same as a uniform moment across the unbraced length. That's like C sub equal to 1, so you're not going to get any benefit there. But if you braced it at mid-span, for instance, you could use C sub equal to 1.3, and that's a big help. It's a 30% increase in the flexural capacity that you wouldn't have otherwise have had if you just said, hey, I'm going to be conservative and use C sub equal to 1 like many engineers do. Okay, on to cantilevers. Sometimes engineers get confused. I know I got confused many times about what do you do with cantilevers? What's the unbraced length? And what, if I want to find C sub B, how do I get it? Well, this next series of slides hopefully answers that question. You always want to brace a cantilever beam at the top flange and the bottom flange at the support. That's just a kind of a good rule. Always do that. And be mindful of the situation where you have a cantilever beam running over the top of a column and a thin web of that beam, because you could get the web of that beam trying to behave like a column and the thing could kick out. So you either want to put a stiffener, a web stiffener there to prevent that from happening, or brace, better yet, brace the top of the column with a kicker coming down from the deck. But anyway, it's important to brace the top and bottom flange at this cantilever support. And then if you can assume you have a free unbraced end with nothing bracing the end of the cantilever, C sub B is equal to 1 for that case. Now, if you have the more common situation where you're bracing the top and bottom flange of your cantilever, but you have something bracing the top free end and the bottom free end, we now can plug into equation F1-1, even though it's a cantilever. We've got two brace points, A and B, right? And we got a moment gradient in between there. So we can plug into that C sub B equation and use it. And if you do that, you get C sub B is equal to 1.67. So if you're designing the cantilever, you brace the free end, top and bottom, and you brace the support, top and bottom, you can use C sub B is equal to 1.67, and you'll get a lot of extra capacity out of that cantilever by doing that. So for cantilever beams, use equation F1-1. And the bracing in the order of preference would be brace the beam with the full depth connection to the cantilever at the support and at the cantilever end. Several different ways to do that, but you're basically bracing the top and bottom flange at the end of the cantilever and at the support. The next best thing to do is put a full depth stiffener and kicker at the support and the cantilever end. And then the next best thing to do would be to put full depth stiffeners at the support and the cantilever end. But there you have to convince yourself that the slab has enough flexural stiffness to prevent rotation at the end of the cantilever. And most of the time, your slab, if it's a 2 plus 3 1/4 or 3 plus 4 1/2, whatever you got out there, will probably be sufficient. If you're not sure, you can use the stuff in Dr. Ura and Dr. Helwich's seminar they tell you what flexural capacity you have to have in that slab to constitute a brace point. So these next examples that I'm not going to go through, you can work them on your own. They just take those three equations for C sub B that I talked about, and they plug into them for different situations. And notice again that they're sign dependent, so you plug into your moments there. If they're negative moments, you put a negative sign. If they're positive moments, you put a positive moment sign. So I'm going to skip through these in the interest of time, but I want to point one case out. This one right here, example 3. I'm not going to work through it, but I just want to tell you a quick story. We got called in as a third-party consultant to a dispute where the engineer of record was claiming something, the peer reviewer was claiming something else, and then they didn't agree, so we got called in as a third-party opinion. And what we found out is that the original engineer had designed this, and he really didn't know much about C sub B, and he came up with an answer. Then the second engineer came in and checked it, and he used C sub B equal to 1 and found out it didn't work. And the first engineer felt like, although he didn't really know what C sub B was all about, he just said, I've done this many times, I think it works. So we started looking at it, and really what we found out is that if you plug into the C sub B equations, and this was a situation where different span lengths, and then there was a cantilever at the end. And the reason this was getting to a dispute, we were talking about 1 million square feet of this. This wasn't just one situation, this was 1 million square feet. So if a correction was going to have to be made, it was going to involve beefing up numerous beams. It would be hundreds of thousands of dollars. So this was a big deal. And just by understanding the flexural capacity and knowing what C sub B was all about and going to the extra trouble to calculate C sub B, we found out that the section worked fine. Whereas the peer reviewer was checking it with C sub B equal to 1, because guess what? That's what he'd always done. So just a little lesson how sometimes this C sub B stuff can really help you. And again, we go through all the calculations here that you can do that in your leisure.